Welcome to this session. This session, we are also going to give another example of numerical differentiation problem. So the question is, the table below shows values of a certain function. So we have the x values and the f of x values. So when x is 1.0, f of x is 2.7183, then you have 1.2 corresponds to 3.9841 up to 2.6, where we have 35.006. So the first question, draw a difference table up to the fifth differences from this given table. Draw a difference table up to the fifth difference using the table given in the problem. So this is how we draw the table. So the first one, you write a column for x values, so 1 up to 2.6. Next one, you draw f of x column, and then you do another column for first difference, second column for second differences, third column for third differences, fourth column for fourth differences, fifth column for fifth differences. So that's step one. And step two, these values of x, you write them leaving a line in between where the differences would be written. And once you have written all the x values and f of x values, to get the differences, is usually you pick the lower number minus the upper number. And then so like, for example, to get this one is 5.6, to get 1.6932 is 5.6773 minus 3.9841. And that's what you work out throughout to get all the differences up to the fifth differences specified. Once you have done that one, so the question in this case is to approximate the value of the second derivative of the value of the function when x is 2.6. Now, when x is 2.6 from our table, which is a value at the bottom of the difference table, you write to specify the diagonal of the differences. So write 2.6, then its value of f at 5.006, and write this diagonal. So values in that diagonal are the ones that are going to help us to work out the problem. And we'll be using Newton backward because the 2.6 is at the bottom. If it was at the top, then we'll be using Newton forward. And if it was a value around the middle of the difference table, then you either use Bessel formulas or Stirling formulas to get a better approximation. So know that values which are, if you want to approximate values at the beginning of the difference table, then you apply a formula involving Newton forward. Values which are at the bottom or near the bottom of the difference table are approximated by formulas for Newton backward, and values which are at the middle of the difference table are approximated by Stirling or Bessel formulas. So after doing the difference table, these are the questions now. Approximate. So part say B, approximate second derivative of the function at 2.6 using the first two terms, three terms, and then 4 terms. So the first thing you do, you have to write the general formula for approximation. So solution, we know that the second derivative of x naught is given by 1 over h squared into second backward of fn plus third backward of fn plus 11 over 12 fourth backward of fn plus 5 over 6 fifth backward of fn. So this is the formula that we apply. Now, first part, 2 terms means we go up to this point here. And one thing that should be clear on this difference table that we are drawing, note that this column is for the first difference. This column is for the second difference, third difference, fourth difference, fifth difference. So therefore, the first term in that formula, which specifies second difference, will be this number. Will be this number here. So this is what you are going to use as our first term in the formula for Newton backward, not this one here. This is the first difference. This is the second difference specified in the formula. So we'll have h remains to be 0.2. So we'll have one f double prime at 2.6 will be approximately equals to 1 over 0.2 squared into this second backward of fn is given by 1.9490. That's what we have in our difference table, and then plus 0.42500. And when you work out this, you get 59.35. And then 2 terms, f double prime at 3 terms, 2.6 will be approximately 1 over 0.2 squared into 1.9490 plus 0.4250 plus 11 over 12, 0.0089. So when you work out this, the answer should be 61.3895833333. And lastly, using 4 terms, so the second derivative at 2.6 will be roughly 1 over 0.2 squared into 1.9490 plus 0.42500 plus 11 over 12, 0.08900 plus 5 over 6 into 0.016100. And when you work out this one, you get 61.725. So that is the answer to that given part of the problem. And lastly, number C, given that f of x is x e raised power x, x e raised power x, find the absolute and percentage error in B above. So the first thing is we have to realize that to find absolute error is a difference between absolute value, the difference between exact and approximate. Absolute error is exact value minus approximate value. So we'll get exact value by differentiating this function twice and replacing 2.6. So f of x is x e raised power x. So let this one to be u, let this other one to be v. So u prime v plus v prime u. So u prime is 1, so e raised power x, plus v prime is e raised power x, so times x. So which is 1 plus x e raised power x. So this is the first derivative of the function. The second derivative, we still apply product rule. So this to be u, this to be v. So u prime is 1. So have e raised power x plus v prime is e raised power x. So 1 plus x e raised power x, which when simplifying we have, or that's what we have. So that when we have to find the derivative at 2.6, we'll just replace where there's x by 2.6, e raised power 2.6. So 2 plus 2.6 is 4.6. So 4.6 e raised 2.6. So this is the exact value of the function. The derivative of the function at second derivative of the function at 2.6. So therefore now A, when we have two terms, or the first Roman one, then error will be given by the exact value 4.6 e raised power 2.6 minus the approximate value, and the approximate value when our answer was approximated by two terms is 59.35. This difference will give you 2.583194,961. So which means that in this case, percentage error will be 2.583194,961 divide 4.6 e raised power 2.6 times 100%. This will be 4.170937673%. So that is the error and the percentage error in the case of two terms. When we have three terms, let's call error epsilon 2. So it'll be 4.6 e raised power 2.6. Approximate value in that case was 61.38958.3333. When you work out, you get 0.543611.628. And you see this one is lower than the previous one. So which means percentage error will be 0.543611.628 divide 4.6 e raised power 2.6 times 100%, which when you simplify, you get 0.8777387124%. You see also the percentage error has also reduced. And then lastly, when you're using 4 terms, so let's call the error epsilon 3 4.6 e raised power 2.6 minus the approximate there was 61.725. This will give you 0.208194961, and this implies, you see also here the error is 0.2, previous step error was 0.5, so the error has also reduced. So percentage error is 0.208194961 over the exact value 4.6 e raised power 2.6 times 100%, which will be given by 0.336160555374%. So also this percentage error has also reduced, and the same trend as what we have dealt with before, that the more the number of terms, the less the error and the better the approximation. The more the number of terms, the less the error and the better the approximation. So to get the best approximation, the better approximation, you have to use more terms. And the converse of the statement is also true. Thank you.